Next topic is, guess what? We had yesterday SDN. It's a very high-flying topic, and now we get some more insight in how you can do automated tests, automated QoS tests. Chris Lauwers, founder and CEO from Ubicity, with lots of experience and in this field will give us some insight. He's visionary, focused, and turns networking, telecommunication knowledge into application and software. And
thank you, Jack.
Keen to hear what you say.
And I promise this will be the last presentation of the week about SDN, so no more after this. So I'm presenting here in my capacity as the co-chair of the UCSDN activity group. And there will be some overlap with some of the discussions that have been going on yesterday, but my goal today would be to provide a bit of a unifying architectural framework, if you will, for how the various SDN activities that various partners are involved in and the activity group itself is involved in, how it all fits together architecturally, and also a little bit more technical detail about how we see the whole thing working and operating. Now, we've talked about SDN quite a bit. I don't think we've actually gone through what SDN is, so I'll try to tell you everything you need to know about SDN in 2 minutes. So I'll do a quick exercise in that, and then I'll tell you a little bit more about why SDN is important for people like us who are, in the end, really just end-user application developers, and specifically developers of UC applications. So we'll talk about what the applicability is of SDN for those types of applications, and we touched on this yesterday. There's applications in automating the quality of experience, or the service quality, as Todd called it. There's a lot of applications in diagnostics, and that's a use case that in the activity group we haven't spent a whole lot of time on, so I won't spend much time on that today either. And then finally, orchestration, which is, I think there's a lot of opportunity there, and that's something that's on the roadmap for the activity group, but we won't report on that today either. So the focus of the presentation today will be on automating quality of experience, or the service quality, and specifically on three aspects of that where we've done a fair bit of work in the activity group. The first one is coming up with mechanisms to automate the QoS marking of voice and video streams. That is related to a second activity, which is around admission control. How do you, in a centralized fashion, decide whether traffic is allowed on the network or not? And then finally, that leads to opportunities in the area of traffic engineering, where you might be able to optimize how the available bandwidth capacity is used for the various sessions and flows that you have going on the network. So first, let's recap SDN. So let's start, what is SDN? Let's start with the official definition from the Open Networking Foundation that says that software-defined networking is the physical separation of the network control plane from the data plane, where each control plane controls more than one network element. Right? And if you look at a traditional network where you have routers, switches, whatever else may be part of your network, each of those devices typically has a forwarding plane that takes packets coming in on one interface and sends them out on a different interface. Now, the decision about where to send those packets to is made by the control plane, and the control plane is the entity that runs the routing protocols, things like OSPF and BGP and what have you. So the routing protocol tries to create an overall view of the network topology, and based on that topology view, it makes forwarding decisions for packets based on addresses incorporated in those in the packet headers. Now, in the legacy or in the traditional network, every single routing element or every single network element in the network has its own control plane, runs its own instance of the routing protocols, has its own view of the overall network topology. So it's a completely distributed setup. What SDN tries to do is take that control plane out of the network elements and moves it into a more centralized or logically centralized control plane, where that control plane then controls the forwarding behavior of the various network elements. So that's SDN in a nutshell. Now, what that drives is an architecture where you have a logically centralized network controller that uses SDN protocols to control the behavior of the various network elements. And the most well-known SDN protocol is OpenFlow, but there's other protocols that could be used to control how networks and network elements forward packets. And, there's even implementations that use legacy protocols like BGP to control the forwarding behavior. But the key here is that this drives an architecture with a logically centralized controller. If that controller wants to make decisions about forwarding, it needs to have an inventory of all the network elements in the network domain that it controls. So it has an inventory module. It needs to have a topology module that knows how these various network elements in the inventory are connected together. Based on that topology, there's a path computation module that makes routing decisions about which end-to-end path to take through those network elements when a packet enters the network with a destination somewhere else on the network. Based on the calculated path, the SDN controller then needs to program the individual network elements to make sure that the forwarding behavior is such that the path will be taken in an end-to-end fashion. And then for good measure, we try to collect statistics from the various interfaces on the various network elements so we have an idea as to whether things work correctly or not. So that's sort of the core of an SDN controller. You've got inventory, topology, path computation, flow programming, and statistics. Now, with this architecture, the real opportunity is to expose capabilities to do things differently than what we were able to do before, right? So if this was just a new architecture to do the same old thing, that wouldn't be very interesting. But the opportunity with SDN and the promise of SDN is that this lets you create new network applications around network management, around service management, around implementing new forwarding strategies or new routing protocols. And those opportunities are presented through a set of interfaces or APIs that are called the northbound interfaces that let SDN applications communicate with the SDN controller. And that's ultimately where the real opportunity is for SDN. Now, as you see application developers or end user application developers, why should we care about that? Because we're not in the networking business. We're not necessarily interested in building new routing protocols or even sophisticated low-level network management tools. But the interest, I think, is around the ability to interface with the network in a much more holistic fashion, just like the people from Meru mentioned yesterday. If you think about it, what ability you have as an end-user application program as it relates to the network, it's actually quite astounding how limited, what the limited functionalities that you have available, right? You have visibility into the network based on your interfaces to the network on the endpoint that you're running on. And those interfaces, you may be able to create some ports on those interfaces, connect those ports to some other endpoint by specifying some address and some protocol, and that results potentially in a connection. But that's about the extent of the capabilities that you have as a network programmer. So the abstractions, if you will, as it relates to the network, are strictly limited to connectivity. It relates to interfaces, ports, addresses, connection, and that's it. And if you're doing UDP programming, by the way, you don't even have a connection concept. You send a packet on the network, and the network is not able to tell you whether it gets there or not. You rely on the application on the other side to tell you that information. So very limited capabilities to program the network, very limited visibility into the network, and that limits what you can do as a software developer when it comes to network issues or network failures. Now, SDN, on the other hand, because of the centralized controller that has these 5 very rich modules, is now able to expose a whole new set of abstractions to software developers that let you interact not just with your interface into the network, but with the network as a whole in an end-to-end fashion, right? So the topology and inventory module will allow you to expose topology abstractions that give you information about where various network elements are on the network and what locations are connected to that network. So you might think about creating information about location, about proximity, about the paths between those locations. And all of that can get exposed through the right set of abstractions. When you create connections through that network, you now have abstractions that deal with the status of the path as a whole, right? So in addition to creating information about link status, you might actually have abstractions that create information about the path status in an end-to-end fashion. You may create abstractions that deal with the performance of traffic flowing through those paths. How much latency am I experiencing? How much jitter am I experiencing? What is the average bandwidth that my connection is receiving? So those types of things with an SDN infrastructure, you should be able to receive those from the network as opposed to having to build all kinds of hacks into your application software to kind of get an idea about that type of information. And finally, there's, with this rich information, you can start feeding that into analytics engines where you get trend information about average usage patterns, potentially based on time of day, based on location, and what have you. So a very rich set of applications, a very rich set of abstractions that allow you as an application developer to take advantage of the network infrastructure in a much richer way than you were able to do before. Now, as it relates to UC, the question then is, so if those abstractions are available, what would I use them for? Or what specifically would I like to tell the network or find out from the network so that I can improve my UC experience? And the real opportunity there is around, it really is around quality of experience, because I won't beat a dead horse. We went through this yesterday a number of times. But we've all been there as UC vendors. You get a support call that says my video conferencing system is not working or your phone is broken. Well, we all know the systems work perfectly well, but there's something going on in the network that causes disruptions in the media flow, and as a result, the experience to the end user is poor. And as UC system vendors, it's a very frustrating experience because we have very little visibility into what's actually going on in the network, and we have even less capability to actually then go do something about it. So the opportunity with SDN is to use the abstractions to find out information about the network and tell the network to do something about it, and then ultimately close the loop between the UC app and the underlying network. So let's revisit what are some of the things that you might want to tell the network if you had the ability, right? If you put voice and video streams on the network, one of the first things you might want to do is tell the network that this is voice and video. Identify the traffic, and that may sound trivial, but that's actually not so easy to do with legacy systems, right, or with legacy networks. The way legacy networks implement QoS typically is by using some mechanism like dedicated voice VLANs to identify traffic as voice or traffic as video. If you deploy a legacy voice VLAN, you know that your voice over IP phones are going to be connected to that voice VLAN, and by definition, all the traffic coming out of that voice VLAN is voice. So that's an easy way to identify. But now what if you have a UC system where you mix voice, video, data, and everything else? Then you need some other mechanism. Network vendors have proposed things and are using things like network-based application recognition, where you try to use deep packet inspection to look in the packet headers to figure out what the payload might be that's contained in that packet. Now, network-based application recognition, in my opinion, is just a fancy technical term for guesswork. So it's not foolproof. It doesn't work when the packets are encrypted. And when you have packets roaming around, that creates a lot of challenges to keeping track how to identify those streams and where they are. So what if instead you could explicitly tell the network, I'm putting traffic on your network between these two addresses, and by the way, that traffic is voice traffic, or it's video traffic, or it's streaming traffic, or what have you. So we believe that you could do a lot better as it relates to quality of experience if you had the ability to explicitly tell the network, here's the type of traffic I'm presenting to you. Now, the second thing you might want to do then is once you can identify the traffic as voice or video, then you can also tell the network, here's how I'd like you to treat that traffic. Here's the QoS treatment that I'd like you to apply to that traffic. And you might be able to do that on a session-by-session basis or even a flow-by-flow basis, as opposed to sort of the one-size-fits-all mechanism that you get from more static QoS configurations. In a legacy QoS deployment, what you would do is, assuming you're accurately able to detect what traffic is voice, you then uniformly apply QoS voice markings for that stream, and it doesn't really matter whether that's voice associated with a telepresence call or a voice over IP call or two people using Skype to make lunch plans, for example. The network has no way to differentiate between those different types of applications. So the one-size-fits-all really doesn't work in a UC environment. Then thirdly, what you might want to tell the network is how much bandwidth you'd like associated with that voice or video stream. And if you then tell the network to reserve that bandwidth for you, you now have a centralized place where you can make decisions about allocating your scarce bandwidth resources to various sessions. Right? So this is what's typically called admission control, but it's done in such a way that you have a centralized entity that has visibility in all traffic for the network as a whole, as opposed to per application admission control, which is typically how UC systems do things today. And by the way, the decisions that you make today with existing admission control systems don't really give you the ability to go reserve network on the bandwidth. It's based on your own application level accounting of how much traffic is going on in the network. So it's typically not all that accurate. And then finally, there are scenarios where you just don't have any available bandwidth at all to accommodate the traffic. So you might want to think about how you can optimize traffic on the network by potentially rerouting some things or what have you. So there's traffic engineering infrastructure that you might want to plug into to optimize the available bandwidth so you can squeeze out more bandwidth and as a result allow more traffic. And you might now actually have a shot at doing that, whereas before, once you're out of bandwidth, you're out of bandwidth, and all bets are off. So those are the types of things we've been discussing in the UCSDN work group. What's a functional architecture that lets you do this? And what are some of the interfaces into that architecture that UC applications could use? So here's the architecture that we've come up with. And again, it's a functional architecture. It shows functional blocks. This doesn't necessarily translate into a software implementation, but conceptually, what we're proposing is that as part of your SDN infrastructure, either running in the controller or somewhere with the controller, you have a new module that we call the automated quality of experience module. And that module has at least 4 submodules. One would be the dynamic QoS marking module. That's the infrastructure that lets applications identify traffic to the network and request QoS treatment for that network. You might have an admission control module that lets you request bandwidth associated with those sessions, and that admission control module would then also regulate access to the bandwidth resources. You might have traffic engineering done dynamically, so you can optimize the available bandwidth in a more dynamic fashion, and then all of this would be governed and regulated by a policy module, because anytime you have resource allocation algorithms or what have you, there's different policies you can apply to decide who gets access to what. So by definition, I think there's a policy capability or component that needs to be part of this. And then we'll have automated QoE APIs that UC system can use. There's an administrator interface that we envision defining at some point, but that hasn't been done in the context of the current activities. Now, as it relates to the interfaces and the use cases, I said there's 4 modules. We don't envision that one would have to deploy all 4 of them to get started with dynamic QoS. In fact, if all you want to do is mark your traffic and identify traffic on the network, you can start with a QoS marking module. So that's sort of the minimum required if you want to get value out of the UCSDN infrastructure. Now, optionally, you could add admission control to that if you want to make decisions about bandwidth. And then a further option would be to add dynamic traffic engineering to that if you want to do dynamic reallocation of bandwidth and rerouting and those kinds of things. So this is how we see a deployment evolution of these types of capabilities. Now, as it relates to QoS marking, let me just walk you through a scenario of how we think this would work. So I'm showing here a fairly trivial network infrastructure where you have a network backbone connected to some branches in a data center. You have UC infrastructure deployed in your data center. You have voice over IP phones or UC systems deployed in some of these branches. And I'll walk you through a scenario of how the various components interact to set up the QoS infrastructure dynamically. Now, the first thing we envision happening is when the UCNC infrastructure first starts up, when it comes up on the network, it will tell the automated QoE service that it wants QoS treatment for all signaling traffic. Right? There may be reasons that you want to protect your signaling traffic or give you signaling traffic priority on the network. So the UCNC infrastructure would do that when it first starts up. It sends a message to the QoE service saying, apply QoS policy to my signaling traffic, and the signaling traffic would be identified based on the protocol that's being used. For example, mark all traffic at port 5060 to the IP address of my proxy server, for example. In return, the QoE server would then communicate based on its inventory of network elements. It would communicate with all the network elements to install the appropriate QoS policies on those network devices. This is sort of a brute force approach. You would proactively install these policies. If you use OpenFlow, you could also use what's called a reactive policy instead, which is the first time a network element sees a packet with the specific traffic patterns or the protocol patterns that you're specifying, you could ask the service what to do with that, and the service could, in a reactive fashion, install those policies. So different ways you can do this based on the OpenFlow or based on the SDN protocols that are being deployed. Now, once those QoS policies for signaling are installed, then your signaling traffic would get the proper QoS treatment. And I'm showing this here in green. So green means that proper QoS is applied. In this case, we're applying class selector 3, just as an example. Now, that signaling traffic on the network with its QoS treatment would get routed typically through your infrastructure, whether it's your SBCs or your proxy servers or your 323 gatekeepers or whatever it is. So the infrastructure has visibility into the payload of the signaling traffic. Based on that signaling traffic, it could figure out where the two endpoints are or where the various endpoints are that will be involved in a call. It could extract that information and inform the QoE manager that we are expecting new traffic on the network between the addresses specified. Please give QoS treatment to that traffic. Now, in the meantime, this is all running in parallel with the call setup. So we're not blocking call setup to take care of all this behind-the-scenes QoS management. So media traffic will start flowing, but it won't initially receive the proper QoS treatment. So that's why this is shown in red, suggesting that all it gets is best efforts treatment. Now, the QoE service would from there then install, based on its topology, it would install QoS policies on the ingress network elements in the network. So the network elements where the traffic from the endpoints enters the network. And once that happens, the traffic would get automatically upgraded to the proper class of service. In this case, if it's voice traffic, you might want expedited forwarding. And the result of that is that you now have dynamically ensured QoS, all driven by your UC infrastructure communicating with the QoE service. So that's a very high-level, quick introduction of how the flow works. From an interface point of view, we proposed in the activity group, we proposed two different interfaces. One we call the session-based model, which installs dynamic policies that are to be applied to voice and video sessions. It's very REST-centric, so you have a create, read, update, delete. For signaling traffic, we have something we call a policy model, which is much more static, and it uses the same REST approach. There's a data model associated with those interfaces. There was a question yesterday about whether that data model is SIP specific. It isn't. It has a notion of a session as a whole, which may have a user associated with them, but the important elements in the session element are the various media elements, because any session, you typically have at least two media streams. You have bidirectional voice, so you have one media stream for each direction. If it's video, you may add one or more video streams, what have you. So you have multiple media elements associated with a session. Each media element uniquely represents a flow that's identified by a 5-tuple on the network, and also we want to make sure we support IPv6, so there's an IP address type field in there. And then very importantly, what we imagine is that the flow would have a requested QoS element that says to the network, here's the QoS treatment that I'd like to receive. And then in return, the network would send back to the UC infrastructure, here's the QoS treatment I'm actually granting you based on either policy or based on available capacity of the network. And it's that interaction between the network, the sort of request response, that lets you optimize within the constraint of what's actually available and within the constraints of what the policy dictates. And in the interest of time, I won't go into detail about the control flow, but the idea is that the QoE service would process these elements. Clearly there's a number of policy items that need to be addressed. We express, or we envision, that QoS treatment is expressed not in terms of low-level QoS markings, but instead in terms of higher-level class of service concepts. So you may have a class of service for real-time voice, for real-time video, for streaming video, what have you. Those classes of services will need to get mapped onto low-level QoS markings like diff-serve code points or WM markings or whatever else, 801.1p markings. But that's up to the implementation and could get done by a QoS mapping. And the specifics of the policy will be part of further work that we'll be doing over the next couple of months. So in the interest of time, I'll just stop here and open it up for a couple of questions.
I wonder how policy will be defined. For example, you have several people in Starbucks competing for video conferencing, the other download the big file from YouTube. How that will be defined?
Well, so the question was, how will the policy be defined? Because if you have a person at Starbucks, you're all competing for the same bandwidth. Someone may be viewing a YouTube video or downloading a big file, where someone else is trying to do a Skype call or what have you. So if you control the network, which is a big if, then clearly you could define that those different applications to different classes of service, which would result in at least different priorities on the network and ideally also different allocations of bandwidth. So if the network is under your control, then that's exactly what this scenario is trying to address. Now, if you're at Starbucks, then clearly the link of the network between your Starbucks access point and wherever you entered your data center, that is a public infrastructure you have no control over, at least today. And the challenge there is, or the question there will be, will there be an opportunity over time for service providers to provide differentiated services, potentially using some of these interfaces, some of these APIs, to let end users or service providers give better quality to some than others. And that's the whole debate about net neutrality. So I think that could be a whole other hour of discussion. I don't think we have time to get into that. But ultimately, I think for UC, I'd love for there to be an opportunity where you could use these kinds of APIs to control things in an end-to-end fashion, even if you run over all or some of the network that's public infrastructure. And I think a lot more discussion needs to be had about that.
Dan?
Sure. Dan Drutz, AT&T. Actually, I have two questions. One was sort of related to that competition for resources, but on the device side. So I think the problem we're faced with is trusting the application that makes the requests. And so I think there's room there for defining what exactly is the level of trust and how that is actually expressed.
Yeah.
And the other thing is not a question, but more of a point. OMA, Open Mobile Alliance, has been working on a QoS RESTful API. I think that fits very nicely with what you're trying to do, and maybe you can.
Yeah, let me address the second one first. We've been working with ONF, so we're not trying to standardize the APIs or the interfaces. Instead, we're working with the ONF, who is in the business of standardizing SDN. And I think ONF has a liaison agreement with OMA, I think. So there's likely some coordination going on there. And we'd love, obviously, for these things to be synchronized and coordinated. As it relates to your first question about security and trust, I completely agree that the network infrastructure shouldn't necessarily trust the endpoints, but you could trust some of the infrastructure components. And so the infrastructure could be a proxy that acts on behalf of your endpoints, and if there's a trust relationship between the infrastructure and your network, then there's a fair number of things you can do. The other thing I didn't get into, just to belabor the point, we envision that there will be low-level information about QoS that will get routed all the way back to the endpoint, so the endpoint has some idea as to what QoS treatment it is given or is granted, so it can take action based on that to change codecs or use lower bit rate or what have you.
Right, but the endpoint, if it's a generic laptop, tablet, whatever, then the issue there is that you got competing applications on the resources. So you either have a local common congestion control mechanism, or you actually restrict the access to these APIs.
But again, the APIs are invoked typically by the infrastructure, not by the endpoint, right? And so we're trying to equip the endpoint with as much knowledge, but not necessarily the ability to go change behavior on the network.
Good discussion. I would suggest to have the discussion at lunchtime for the sake, or is it something short, Russell?
It might be. I don't know what the answer is.
I don't know. We
So I'm kind of curious about the user experience at peak traffic, because we all know from driving cars that once the roads are full, there's nothing you can do, right? So presumably the endpoint will get some feedback saying, you know, you can't do a video call now. It has to be voice, right? Presumably. But what happens for the calls that are already in progress? You know, maybe a bunch of people using the network, and then at 10 o'clock on Friday, it's the CEO's weekly status video conference, right? Do all those just get dropped on the floor because he's got higher priority?
Well, the easy answer is, well, that's a policy decision, which is up to the implementers. Now, clearly that might not be a very reasonable policy action to take, but we didn't get into any detail around the admission control module, but the admission control module could decide that if there is a telepresence call that your CEO runs for the entire organization, well, that has priority and maybe you need to free up bandwidth by kicking off some calls. That information would be transmitted all the way to the endpoints, and the endpoints would have to present that in a user-friendly way so that everybody knows what's going on. But in the end, what we're describing here is mechanism. How that gets regulated by policy, I think we're not necessarily specifying that. We're leaving that up to implementers. But the assumption is that with this infrastructure and this mechanism in place, that we can improve on what you would do today, which is nobody knows anything other than everybody's sessions will be degraded and nobody will have great experience. Right, so we'll at least be selectively able to deal with the high priority sessions and make sure that those are treated with the appropriate quality level. All right.
Okay, thank you, Chris Lauwers. Very interesting topics about SDN.